Welcome to Pattern Analysis. Today we look at one particular instance of model combination, which is tree-based, and then we extend this to the very famous random forests. Let's go. So the Gaussian mixture models that we looked at are an example of a model combination of k individual Gaussians. So we sum them together. And the benefit of such a model combination is that a single Gaussian is a relatively simple model. So analytically, it's well understood, tractable computationally. Usually it's well tractable. It's also interpretable from some perspective, if you like. But then the sum of such Gaussians can also form very complex, very expressive distributions. So in that sense, you start from simple building blocks and put them together to a combined, potentially very expressive model. So you can look at this as a design principle, the model combination. And if you look around in the literature for machine learning, it occurs everywhere. For example, if you think about neural networks, you can say, well, okay, what is a neural network? Neural network is essentially a stack of linear regressors and a nonlinear threshold function combined that you stack on top of each other, and the stacking happens like a million or billion times. There you go. There's your neural network. This is not a class about neural networks, but I want to talk about a second very famous combination principle, and these are so-called tree-based models. So in tree-based models, the combined model is a hierarchical connection of simple basis functions, like, for example, voting-based classifiers, linear regressors, Gaussian densities. And the associated training objective greedily combines these basis functions. In order to avoid overfitting, the whole combined model is then extensively regularized. We're going to talk about this in a second. And the most famous result of this, or variant of such combined hierarchical models, are the so-called random forests. Oops, sorry. Okay. There's a literature reference associated. There's a paper on StudOn by Kriminisi, Schotten, Konukulu. This is the main source for our conversation today. You can also have a look at the book by Hastie, Tibshirani, Friedman, section 15.3.4 and 15.4.3. Let's go. Okay, here's an introductory example. So let's say we have a supervised classification task given some training data here. So we want to distinguish the red circles and the blue squares. And there are different possibilities, of course, to do this classification. The whole pattern recognition class talks about it. But in terms of tools that we got to know in our pattern analysis class, we could say, well, let's start with a representation, histogram representation, to look at these individual distributions. So in other words, we have a equidistant subdivision of the space into these bins. We have the bin boundaries that I just highlighted, and then we can check what falls into one bin. Like here, for example, we have 3 red samples and 1 blue sample falling into one bin. So we can say, okay, in the first bin we have 3 red, 1 blue. And then based on that, we could, for example, build a classifier that would say, well, okay, in bin number 1, we have the majority red. So we can call this red. You know? In the second bin, there's 50-50, so we don't know. The third bin, we have 2 reds, 1 blue. So it's again a red bin. Then we have here a lot of blue, so it's a blue bin. And here again we have 50-50, so we don't know. Yeah? So if we don't know, let's make a dash here. Good. This is fine, this works, but if you look at the data, you think, okay, maybe you can do better. And of course, there are many alternatives. We could use a kernel-based estimator, for example, that would already give a better result here. But I want to look at a tree-based solution as an alternative. And what would that bring? So that would lead to something that is similar to a histogram, but with an unequal subdivision of the space. You know? I mean, this is kind of an artificial example, but still you see, like the bin width here has different sizes. You know? So what are we doing here? We take a super simple, like atomic representation, the histogram bins, and we arrange them into a tree. And what we do during training is that we look for good separation locations for these bins. Yeah? So we come up with separations here, 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 here. Yeah, so, and this in a hierarchical fashion. So the most famous implementation, arguably, of individual trees are so-called classification and regression trees, also abbreviated as CART, or CARTs, in plural. Classification and regression trees. And these classification and regression trees can then be ensembled and with like additional regularization in form of randomization, and then it's called a random forest. And we go through these possibilities like one step after another. So we start with classification and regression trees. The idea of a classification and regression tree is to recursively subdivide the sample space, and then in each partition, so in terms of a tree, this is the leaf node then after splitting. In the leaf node, we do the target class task. So that could be a classification, that could also be a regression, and later we will further generalize this to density estimation. Yeah? But CARTs, originally, the name says it, classification and regression trees, says, okay, like the target in a leaf could be a classification or regression locally in each partition. So, and in that sense, it's very similar to a histogram that you say, okay, like what do I have in that partition? And based on that, I return, for example, a relative frequency for classification. The subdivision of the space is represented as a binary tree, so you always split an internal node into 2 parts, like left and right, you can say, no? And the split can be as simple as thresholding along one of the dimensions. Yeah? People have been experimenting with more complex functions for splitting, but at the end of the day, the simple functions do have benefits. Yeah? And this is in the spirit also of having a basis of simple functions, and the magic happens through the combination of these simple functions. So not through the complexity of the individual functions. You know? Okay, so Yeah, so the left and the right successor nodes, sometimes they are called left and right part. Yeah, you can, in a 1D space, it may literally be the left and right part, but in a more abstract sense, you can also say, if you think about the binary tree, having two successors in an internal node, this also corresponds to a left and right child then of the inner node. Okay, and then in the leaf nodes, like we do the splitting, and then in the leaf nodes, the actual task on the sample is performed. For regression, you can just return the average of the node samples yi. For classification, you can return the relative frequencies per class in this region, so in this histogram bin in a way. Yeah. Down here's an example for regression. So let's have a look at the first picture. So we have a 1D space. X is the position in that space, and f of x is the regression target. Yeah? And we have some function here that we want to represent with the model. Now, the idea of a classification and regression tree is to learn where it's good to split. Yeah? So we can say, okay, let's split here, and let's approximate the left part with a function like this, the right part with a function like this. Works reasonably well. Or let's continue, and it works well, but okay, let's continue the splitting. So if we further split here, we can approximate the left part like this and the right part like this. This is already a pretty good approximation. On the right hand side, if we split here, we can approximate the right part here also very well with a single like fixed value always. No, the left part is still a bit of a problem in terms of approximation. So let's split again. If we split here, then we can approximate the left part like this, the right part like this, and we have a full description of that function. No? And this tree structure, this is what is shown here in the second picture. So we have a root node and it splits at threshold θ1, which is exactly this location. Then it has a left and a right child. So the left child splits at location θ2, which can be, for example, exactly this point. And the right node splits at θ3, which can be exactly that point. And then, for example, we can have a further subdivision in the left child here, which is the final remaining split. Yeah. So if we just abstractly write this as a tree, when you see in yellow the internal nodes here, and in green the leaf nodes. So each internal node has a threshold, a splitting position at a threshold along a certain axis of the input space. Yeah? In 1D, it's always the same axis, but here's an example of a 2D space just to drive this point home. And it's not regression, it's classification. You can literally just mix and match these things as you need it. So here we have a two-dimensional input space. We have these circles and crosses. And what we're seeing here is we have a first split along axis 1. This is θ1 at location θ1. Yeah. Then the left child has another split along another axis x2 with threshold θ2. The right child has also another split along the axis x2, but this is coincidence, could also be a different axis here. It doesn't need to be the same axis at every level. It's totally independent. And then maybe the, like whatever that is, left child or so, is split again along the axis x1, which in the result creates a situation that up here we have a solid majority of red samples. We also see we have a majority of red samples. Here we have a majority of blue samples, also here, and in the remaining part it's not so clear. So I don't know what, it's like a blend, maybe slightly more reddish. I don't know, we would have to count more properly, but let's assume it's more reddish. Then this would be the space of our like posterior, the landscape of our posterior, that we say in the top left it's more red, in the bottom right it's more red, and then in the middle we have a strip of the blue class. Okay, how does the training work? So inner nodes have two parameters to perform a split. The dimension of the feature, so along which axis do we want to split and at what position do we want to split. The leaf nodes, they have as many parameters as we need to describe the task. So if it's a two-class classification, we can describe this with one parameter, which is a relative frequency of class 1. And for class 2, then we would have 1 minus the relative frequency of class 1. For regression, what we saw, it also can be a single parameter if we estimate one constant value per leaf node. Yeah? We have a hyperparameter. This is the tree height, maximum tree height. So we don't grow any path in the tree longer than that maximum tree height, which is just a very elementary tool to control model complexity. And other than that, we can say, well, okay, let's start to build that tree. And building that tree is a greedy procedure, meaning at every level in the construction of the tree, we start at the root. At every level, we simply choose the best solution that we find in that current situation. But we are not making a deeper thoughts like, if I now split here and then I would split there, then it's maybe even more optimal or so. This is not what greedy is. Greedy means that you, from the current situation, you make the best choice without considering other partial solutions in your problem domain. Yeah? The advantage of a greedy approach is it's simple, it's fast, and in many situations it works. So what do you do? At each node, you can do an exhaustive search for the best split with respect to some objective function Q M for that tree. We will look at examples or specific instantiations of these objective functions on the next slide. For the time being, let's just assume that we have an objective function to determine the quality of a split. And then you recursively repeat this until either you hit the maximum tree height or if only few samples are left in this branch. And then there's a second step, because actually this greedy strategy, I said oftentimes it works, but it's also not so good from a global perspective. So there's a second step here to prune the tree. So pruning means like to cut back some leaves of the tree. And the idea there is, okay, maybe we split, but some of these splits maybe do not bring such a big gain in performance, whatever the task is, yeah, either classification performance or regression error of the approximation. So the idea of the pruning step is to remove some of the subtrees again if the additional number of parameters doesn't bring a good improvement in the actual task, in the objective function. So the pruning objective is, in that sense, is a very classical trade-off here. We see it in equation 1. We go over all regions. M is the region index, so every partition in our space. So you can say every leaf also that is described here in that space. And you evaluate the gain in classification accuracy for that region, but you also take into account the number of terminal nodes in that region. Yeah. So if it's literally just one region, then it's one terminal node. But you can recurse this over subtrees. So let's say we have a subdivision of the space like this, no? Then you can say, okay, first I check like a single region. Okay, good. I mean, it's just a leaf node. But then you can also check the combined region here. So this is one internal node splitting into two regions. And then you can say, okay, so I have two terminal nodes here, two leaf nodes here. And my split improves in terms of quality. It only improves by so and so much. No? So is this really optimal or not? Yeah. And so this is a global objective here. The cost function for a partial tree T plus the number of parameters of that partial tree moderated by some balancing factor alpha. Yeah. And if it turns out it's cheaper to remove subtrees with respect to that objective, can maybe check that whole subtree also. No? If it's cheaper to remove that, then let's do so. No? And this is the pruning step that runs through that. This is a particularity of the classification and regression trees. The pruning will not take place when we talk later about the random forests. So in that sense, since the classification and regression trees are superseded by the random forests, it's an operation that is like today in practice is not commonly performed, no? But I think it's good to know. Okay, the objective function. So if the goal is to perform regression, then the objective function QM can be as simple as a squared error. Yeah, where you say, okay, I look for every sample in region M, and then I take the average value of these samples in that region. This is my regression prediction, let's say. Yeah, and I calculate the squared error to each of the actual values here in that region. And this is, so it's very straightforward. For classification, it also doesn't need to be super complicated. Negative cross entropy is something that you're probably familiar with from a different class, or different classes. How does it work? you go over all possible classes in one region. So it can be a 2-class problem, can also be 3, 4, whatever classes. And then you take the probability of having that class, is just the relative frequency of observations for that class number that you have in the box. You count. Yeah? So I have 5 out of 12 are blue. So then it's 5 divided by 12 times the log of that relative frequency. And you sum this up over all classes. You know? So K is the number of classes, PMK the relative frequency of class K in region M. Here, if you have a very clear majority for one class in a region, then it's better, no? Because it gives you a clearer classification result. An alternative to the negative cross entropy, and maybe not so super well known to you, I don't know, is the so-called Gini index. Gini index takes the relative frequency of class K in region M and multiplies it just with the counter event. So what if it's class K times what if it's not class K, and sums this up over all K classes. Yeah. Also here, it's better to have a relatively a good majority for one class in a region. So, given these objective function, when we grow the tree, we have to check different candidate positions, yeah, for the split. So in that case, the overall objective for growing the tree is to search for a candidate split with minimum loss in the left part, so the left child that would be created by that split, plus the right child that would be created by that split, moderated by the relative number of samples in the resulting left and right split. Yeah? Why is this important? It's important because you can have a very nice, very clear subdivision of a region that just splits off a single sample. Yeah? So so if you have a situation like this, and then you say, oh, I make this decision that I split here, so here I have 100% dark green. Yes, that's true. But still, it's not a very helpful split, because like this one single observation, yeah, it doesn't really, so it's not statistically very robust, it's not very useful to only split off one training data. So in general, there should be an encouragement for bigger splits if it brings a little bit of a quality gain also. So that is why we have the product of the quality in that split and its significance, you could say, or the relative number of samples as a proxy for significance. Is not a significance test, of course, no? That jointly is optimized for the left and right split. So the left and right split should both have a certain magnitude and should bring a certain improvement with respect to the overall goal. Yeah. Okay. And here's from our book, from Hasty, Tibshirani, Friedman, is a little plot for these error functions. What we see here is the Gini index and the entropy as nonlinear measures, and as an alternative, the misclassification rate as a very not vary, but as a linear measure over different input or relative frequencies p from 0 to 1. Here in the caption it says the cross entropy has been scaled to pass through 0.5, 0.5 for better comparability. So they all meet here. Yeah, that's one technicality. And this non-linearity of the negative cross entropy and the Gini index, they are actually useful in making a preference for splits that create more sparsity. There's a numeric example in our book here in this section on the trees in Hasty Tip Shirani Friedman. We will also look at this in our joint meeting together to better understand this behavior. Yeah, so this is why the misclassification rate is not used here, but instead the Gini index or the cross entropy. Okay. So you grow the tree, you grow, and then the actual prediction in the leaf node for classification is just the relative frequency, and for regression, you just return the average of the data points in the region. There's a typo in the region. I changed this in the slides. Okay, so these were the classification and regression trees. Let's extend this to random forests. A limitation of the classification and regression trees were super famous. But a limitation of classification and regression trees is that they have a tendency to overfit. It's just hard to control overfitting, even with that pruning step, even with this maximum tree height criterion. If you aim for a tree with high accuracy, high training accuracy at least, then it turns out that they subdivide the space into too small regions, and then they don't generalize anymore to other data. An alternative to this are the random forests, or it's not an alternative. I think it totally makes sense to think about random forests as an extension to cards that add ensembling on top of the classification and regression trees. Random forests are really useful to know also from a practical point of view, because they are still used today if you're looking for a simple high performance model. So something that is below the complexity of a neural network classifier, then random forests are really a super solid choice also in today's times. A core benefit of neural networks over random forests is that neural networks can learn the feature representation. Random forests are only classifiers. Neural networks learn features and classify. So what people also did is that they say, let's take a pre-trained neural network as a feature extractor and then put on top of it a random forest for the classification part. It's also a very common design choice. So then you run the neural network on some dedicated inference chip, but you can have the random forests. You can maybe even retrain them on the fly. It's fairly cheap, and can have this as a more flexible classifier maybe. No? So these are all design options that are on the table. So random forests do have relevance in systems that are used today also. Okay. So what is the idea? So we talk about an ensemble. An ensemble is a collection, you could say, of similar classifiers. And each of these classifiers gives a vote, and the vote is then averaged. And this is the ensemble posterior, or the output of the ensemble. Yeah? Okay. And effectively, these votes come from individual cards, so individual classification and regression trees. And now you say, okay, like if I have a number of classification and regression trees, how can I reach a situation that this voting is somehow meaningful, that it adds some benefit? And the reason for this is that in that ensemble, each of these cards is trained a little bit differently. So this ensures that there's a certain diversity in these ensemble members, and this diversity is then brings this actual benefit, counters overfitting, and so on and so on. So how is this diversity created, or how is this different training procedure achieved? So the idea is to randomize the data and the parameters. Yeah, there are three options on the table for that randomization. The first one is bagging. Bagging is a technique where you say that for training one of the trees in the ensemble, you randomly sample a percentage of the training data. You just assume a uniform distribution over the training data points, and you set as a hyperparameter, I want to have 70% of these training data points, or X% of these training data points. You randomly draw them, train a tree. If you train the next tree, you again, independently from what you did earlier, again randomly draw your X%, 70% of the training data, train that tree. And so on, until a number of trees are trained. So the remaining two options are within the training of a tree. So the bagging selects the data for the training, but also in the training you can do two options. So one is what I call here random subspace selection, that for each node, when you look for the best split, you don't search all possible dimensions, but instead you say the search is limited to D random dimensions. Yeah? And this can be as few as one. Yeah? That you say, okay, now I randomly draw one dimension along which I plan to split now. Yeah? Or it can be something like 2. Yeah? So the next split shall come either from this dimension or from that dimension. So in that sense, you can already think, so this is not going to be a globally optimal split. Yeah? It's just the best split that was available in those dimensions that were randomly drawn for the current node. And the third option is to make it even more arbitrary, you could say, by saying, well, even along those dimensions that I'm searching, I do not do an exhaustive search for the best split there, but instead I randomly select the best split from randomly drawn splitting candidates. Yeah. So randomly drawn split candidates, and so for example, you say, let's check these 10 locations, and we just pick the best one from these 10 locations. So So all these three choices reduce the performance of the classifier. Yeah. So the performance goes down of an individual tree, but at the same time, an individual tree clinches less to the specific input data. Yeah? And as long as the tree itself is better than guessing, yeah, an ensemble of many trees then can still lead to a good result. Yeah? We will talk about this more in a second. However, in any case, what you can say is if you think about the ensembling, the randomization and the ensembling, you can say this is a way of regularizing the output of the model. Yeah, it's a particular way of regularization that maybe if you attended a class on deep learning is maybe best compared to the dropout procedure as a regularizer. Okay. So what is the idea behind randomization? Randomization adds statistical independence and decorrelates the trees. Yeah? So it decorrelates the tree. The statistical independence of the outputs. Yeah? It's statistical independence in the sense of like earlier in our lecture, but on the outputs of the tree. So if we are averaging the votes of n statistically independent and identically distributed learners, this is an ideal concept, yeah, but each of them is better than guessing, then this reduces the variance effectively down to zero even. No? So you have the variance of an individual learner. If they are statistically independent and identically distributed n learners, then the combined variance of the output is 1 divided by n. No? Now if these learners go to infinity, then the variance of your estimator goes to 0. It's variance in the sense of bias variance trade-off, yeah, that we discussed earlier. However, it's not so that we have statistically independent and identically distributed learners. Yeah? Let's have a look at bagging. If we use bagging, then we get identically distributed learners in the sense that they get data from the same underlying distribution of training data, and the training data hopefully is one instantiation of the real-world distribution. Yeah? They are identically distributed, but the procedure of bagging it has some overlap. Yeah? So several trees will reuse same data points. Yeah? Not all of them, but if we randomly draw 70% of the data, then already with 2 trees we will have an overlap in the data. No? You can say, okay, I reduced the percentage, but then no matter, whenever you add enough trees, sooner or later you will have some overlap in the training data, and this breaks statistical independence. No? And instead it introduces a correlation row between these learners. No? So if you now do the same thing, if you say, I go to n to infinity, no? What happens then? The variance of your learner, part of the variance is indeed reduced to 0. So we have one part here that says this part that is not correlated. So 1 minus the correlation. This tends towards 0. if n goes to infinity. Yeah? So here the variance, this variance that is not part of the correlation, is indeed effectively reduced, but we remain here with a floor, let's say a variance floor in the order of magnitude of that correlation between these learners. Yeah? So the variance is at least rho times sigma squared. You can say, yeah, okay. But we're not only doing bagging, right? There's also this random subspace selection. There's also the random selection of splitting locations. And this is exactly the point. Yeah? So these remaining randomization steps, they aim to further reduce this correlation rho. Yeah? So they say we willingly accept to weaken the individual learners if only their correlation is reduced. So if every learner has different splitting positions at every level of the node available, then shouldn't this help to decorrelate the result? And the answer is yes, it does help to decorrelate the result. Okay. But it's difficult to quantify the exact amount, so I didn't dig deeper into this theoretical consideration here. Okay. If you think about your random forest package in terms of parameters, hyperparameters, the configuration of this randomization, these are additional hyperparameters. So you have a bagging percentage, you have a certain number of dimensions that you randomly choose from in every node, and you have a certain number of candidate splits per dimension that you are considering. Okay, let's have a look at the impact of randomization on the posterior, so on the prediction of the forest. Yeah, we have a very, 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 very simple training problem here, which consists of a yellow class here in the top left and a red class in the bottom right. This is from the paper by Cremonesi, Schotten, Konokolu, by the way, that is on StudOn. So let's train trees that are super simple as well. So every tree consists only of a root node, and that does a single split and the two resulting leaves. Yeah? With the randomization in place, random splitting positions, random splitting dimensions, and so on and so on. Like this separating line that we see here, for example, it could be at many different places. Yeah? Here it happens to be here. For the second tree, it happens to be along the other axis over there. Yeah? And the effect that this has is shown in the row below. So here is the posterior shown for one tree, 8 trees, and 200 trees. And what we see is that for one tree, we have a very sharp step in the posterior. This is bad because if we have an input that is close to the boundary, if we add a little epsilon to that input, we might push it over the boundary. Yeah, so it's like plus epsilon. And then it has a huge change in the prediction outcome. And this is undesirable for many reasons, like across engineering, numerics and whatever. So we don't want a system to have, like if the input changes only a little bit, to suddenly jump in the output. Yeah? If we look at the variance with more trees, because there are different splitting positions introduced here, and the posteriors are always averaged between these trees, what we're seeing here is an increasingly smooth transition from one class to the other. Yeah, so for 8 trees, it's kind of, I mean, it's already much better, but there are still like recognizable steps here. For 200 trees, it's like a super smooth transition from red to yellow. No? And then this is actually a very, very desirable behavior of the posterior here. This is a figure, as I said, from the paper. If you want to have a closer look, please have a look at the paper that is on StudOn. Okay, so there are a couple of further remarks that can be made on these random forests. First of all, if you do bagging, then you can save data for cross-validation, which is actually a very nice feature. No? So you don't need a separate validation set, because if you only use a percentage of the training data for training one individual tree, you can say whatever percentage is left over, if you use 70% for training that tree, 30% of the data are not used for that individual tree. So you can say, as a validation set for that individual tree, I use this 30% of the data that I have not been using for training. And these are so-called out-of-bag samples, OOB. Samples that can be used for validation. Is a nice little side effect of this overall procedure. Generally speaking, if you increase the number of trees, then you improve the variance down to that correlation floor, of course, which directly translates as a counter to overfitting. On the other hand, if you aim for more expressive trees, oftentimes you need to do this. It depends on the application. Deeper trees increase the risk to overfit. So it makes sense to set a depth limit. That's the first thing. Usually you don't prune the random forests. So this pruning step of cards is omitted. You just regularize with these randomizations. But if driven from the application, you have to go to a certain depth, then in any case, it always makes sense to try out to increase the number of trees. Okay. The implementation is very parallelization friendly. You can just map individual trees to separate compute nodes and then train them separately. They don't influence each other, so it's very useful. What is also useful is that you can directly use them for multi-class classification, because at the end of the day, these relative frequencies, you can calculate them for an arbitrary number of classes. And this is a clear advantage over other traditional, let's say, classifiers, so classifiers other than neural networks. Because, for example, in support vector machines, by design of the problem, and I mean, you're aware of this from the pattern recognition class, you always have a 2-class problem. And then if you have a 3 or 4-class input, you suddenly have this difficulty, the need to somehow bend a intrinsic 2-class classifier into a multi-class scenario. You don't have this problem with random forests. So random forests are really a solid choice if you want to go somewhere below a neural network type of effort. The decision boundaries of so-called extremely randomized forests, so forests that use this full suite of the 3 randomization options, they are very smooth. And this oftentimes improves robustness, because smooth posteriors are in many applications what you want to use. There's also a line of work that argues that trees and forests are oftentimes used for explainable decisions, because you can essentially walk down that decision tree and see what it did. I'm just mentioning this for the sake of completeness. I'm not the biggest fan of this perspective, because I would say this holds for all composite classifiers. So in principle, it also holds for a neural network. You could say, oh, well, a single neuron is just a linear regressor and a threshold. So it's also explainable. The problem with explainability comes if you scale the problem size up. So if you have many trees in a forest, or if you have a deep tree with many decisions or so, then everything becomes unclear. And this is also true. And this is the same problem then as what we're seeing for neural networks, which are oftentimes blamed for not being explainable. I mean, they are not explainable, I would agree, no? But I would sort of disagree to say, why don't you use a random forest? It's much more explainable. I'm not so sure about this. But if you look through the literature, you oftentimes see such a statement. So we talked about it. Okay. Here's a nice little aspect from our book on, from Hastie, Tibshirani, and Friedman. And this is a perspective to say a random forest can be seen from some perspective as a nearest neighbor classifier with adaptive support. So this comes back to our initial motivation to say, can't we use a histogram with varying bin sizes? Yeah? You can say, yeah, why not? You can also draw this analogy to the nearest neighbor mechanism. Yeah? So in the random forests, you have this behavior that you dynamically split as long as you have enough samples in an area. So this means denser areas are probably split up more often. So you have a smaller area of support, and sparsely populated areas are split more rarely. Yeah? And here's a little comparison from our textbook. On the right, we see a 3 nearest neighbor output on that data. On the left, we see a random forest, I think without the subspace splitting and without the extreme randomization, only with bagging trained. And but you can look up the details in the book. But in any case, what the authors point out, and it's also interesting to observe, is that there are sometimes these very long lines, axis-aligned lines, which come from the fact that these splits that we're doing are essentially thresholds along one or the other axis. Yeah, and in a pure nearest neighbor classifier, you would not see this, but I would say from an implementation point of view, so it doesn't make any difference. Okay. So once we understood that we can use a card or a random forest with a regression or a classification objective, we can also say, well, can't we replace this also with some unsupervised objective function, no? And maybe perform density estimation? And the answer is yes, why not? No? The authors of our paper call this a density forest. Yeah, good to have a name for it, but essentially it's a random forest just with a different objective for the training. You know? So an unsupervised loss can use the structure of the data, can only use the structure of the data. And the idea, like what structure to use, is, for example, to say we look for splits that create compact Gaussians. You know? Because this is something that we can fairly easily quantify. We can say, okay, if I would split here, let me draw this really quickly. So we have the space, we have the data points, and now we can say, okay, if I would split here, so this is one candidate, then I can calculate a covariance here, I can calculate a covariance there, and more compact would be better. Yeah? It would be a better split if two more pointed distributions come out of this. Yeah. So in order to assess the compactness of this Gaussian, one can calculate the determinant of the covariance. And that's it. That is the objective, actually. Yeah. If we look at this function, we have a couple of constants in front here. These are just constant factors that don't really matter for making a choice. Is this split better, or is this split better, or is that split better? And then we have here the covariance of the samples in that region. And here we have the determinant. Yeah? So this line here is the determinant operator. No? Okay. So determinant of the covariance matrix has a geometric interpretation. So in that case, it would be like a box, like the volume of a rectangular box around the majority, let's say, of the samples. Like, I forgot, like 1 or 2 standard deviations around the sample. Okay, so here's what it looks like. You use this objective, and then you get a tree out of this, and here's a visualization of a single tree model. You know? So a tree then represents itself as a spatial collection of truncated Gaussians. Yeah? So we have Gaussians here in each region, but at the boundary of a region, the Gaussian is chopped off, because then there's a different region, so a new Gaussian starts. Yeah? So we have these piecewise Gaussians, you could call this. No? Okay. So here are different, like, just rotations of the same piecewise Gaussian, just to illustrate what it looks like. And then you can say, okay, these I can see that this kind of becomes something like a density estimate, but there are these discontinuities. And these are the same discontinuities in the posterior that we saw already for the classification. We would also see it for the regression. Yeah? So they are smoothed out. These discontinuities are smoothed out by using more than one tree. So if this becomes a forest, if you have many trees and you average over them, then this is smoothed out. Yeah? Here's a little example. this actually goes over the depth of the trees, not the number of trees. But here it shows, like, if you have a very shallow tree, then these Gaussians are very wide. If you make the tree deeper, then you have more Gaussians to more directly describe the data distribution. So it has a depth of 2, depth of 4, depth of 6, which again shows a bit like deeper trees have a tendency to fit more tightly to the data, no? Yeah, you can use more trees then in order to counter the overfitting a little bit. Okay, so how can you sample from a density forest? You can do ancestral sampling, very much in the spirit of what we saw earlier in the lecture. So density forest, you can say it's a non-parametric estimator if the number of trees goes to infinity, but I'm not so sure. If you sample from that data, what you can do is you can randomly select a tree, then randomly move from the root to the leaf, descending to the left with the probability that equals to the relative number of samples that is covered in the left branch. And the counter event 1 minus that relative number is then the probability to go to the right branch. You randomly sample from the covariance in the leaf. And in the sense of rejection sampling, you have to this random repeat step 1 until the drawn sample is inside the leaves region. Then it's like literally like a rejection sampling procedure. No? Okay. Yeah, you can also use this framework of the forests in some bigger context. Yeah? And for example, if you check the paper by Cremonesi, Schotten, Konokolu, what they are describing there is a so-called manifold forest. And a manifold forest, turns out, is just a density forest where on top, so they use the density to calculate affinities and plug these affinities into Laplacian eigenmaps. So, and then what you have is you have a mechanism to learn these affinities with the random forest principle, let's say, no? Learning idea, and then use these learned affinities for dimensionality reduction. So the density forest can be combined with a graph Laplacian L to achieve an alternative formulation of Laplacian eigenmaps. So how does it work? We need to define an affinity matrix WT because like for every tree such a matrix is produced, and the core component of this affinity matrix is essentially a distance that is defined between two samples. So an affinity Wij in that tree is defined as e raised to the power of minus the distance between two samples xi, xj. No? Okay. So how can we define this distance? There are two possibilities. There are probably more, but here are two reasonable possibilities. One, which probably intuitively would come to anybody's mind, is to say, well, let's use a Gaussian affinity. No? So we can say the distance between 2 points is essentially the squared difference between them, moderated by some standard deviation sigma squared. And this is calculated if xi and xj are in the same leaf. Yeah? So then you take that Gaussian distance. And if they are not in the same leaf, if they are in different leaves, then the distance is infinite. If you plug this into the function up here, yeah, if they are in the same leaf, you have exactly the formulation of a Gaussian without the normalization. If you plug infinity in there, then you have e raised to the power of minus infinity, which is just 0. There's no affinity between samples that end up in different leaf nodes, and there's this Gaussian affinity for samples that are in the same leaf node. Now, if you say, okay, can I further optimize this? Here's a binary affinity. Binary affinity is super radical. So it says if two samples are in the same leaf node, let's just give it a distance of 0 and let's give it a distance of infinity otherwise. So again, if we look at here our distance function, e raised to the power of minus 0 is 1 and e raised to the power of infinity is 0. So this is why it's called a binary affinity. So either 2 points belong together, then they get an affinity of 1, or they don't belong together because they end up in different leaves, so they have an affinity of 0. If we think about this in terms of an adjacency matrix, WT, yeah, then we can say, well, we can rearrange the nodes in an order such that we have these block matrices. Yeah? So we just renumber the nodes. This is a permutation. Yeah? So we permute the nodes such that in leaf number 1 we have our samples 1, 2, 3. Then they form a block like this. In leaf number 2 we have the samples 4 and 5, and so on and so on. So we order the samples by their membership to a leaf, and we obtain such a diagonal block matrix. And all the off-diagonal entries are 0 because we have 0 affinity between a sample from one leaf and another leaf. Yeah. So here this is 0, and so on. No? Okay. Now these affinities are all discontinuous, which would create a problem for the Laplacian eigenmaps. But we have the averaging again, which smoothes our posterior. In this case, it smoothes our affinities. Yeah? And this removes the block structure. Yeah? Because if we have different trees, they have a certain diversity. Yeah? So they are trained on slightly different data, slightly different conditions. So it could be the case that there's one tree that somehow combines the data like this, like this, like this. No? Maybe there's another tree that combines the data like this. Yeah, I mean, I'm inventing things here, obviously, but so they all have their different subdivisions. So this kind of creates these affinities like along that manifold here by averaging these values. Yeah? And affinities are larger or will be larger for sample pairs that oftentimes, like for many trees, end up in the same leaf node. Yeah? And they will be lower when they just more seldomly end up in the same leaf node. And this creates a sense of locality. Yeah? that is learned from the data. Okay. So, and then you can say, okay, perfect. So then I have a weight matrix W averaged over all the affinity matrices from the individual trees that I can directly use to construct the Laplacian L. No? And then, just for the sake of completeness, I'm mentioning in the paper, if you check, the graph Laplacian is a bit differently normalized than what we were using in our Laplacian eigenmaps paper, but it's not a big deal. It's effectively the same thing, but what the authors in this paper propose is to use an identity matrix minus, then we have the diagonal again, diagonal of these affinities raised to the power of minus 1/2. So effectively you take the square root of each diagonal entry. So 1 divided by the square root of each diagonal entry times W times this particular matrix D raised to the power of minus 1/2 again. But it has the same effect. And then you can reduce the dimensionality of the data. So far in the manifold learning section, we only discussed Laplacian eigenmaps for a mapping onto a one-dimensional space. Let's just go quickly through what has to be done in order to map it to more than one dimension. Very same approach as for the Laplacian eigenmaps. You sort the eigenvalues and associated eigenvectors in increasing order. If you have disconnected components, for each disconnected part you will have an eigenvalue of 0. You just discard it. And you start with the lowest non-zero eigenvector. And then you say, okay, I want to map it onto d prime dimensions. Yeah? So you take the eigenvectors, E1, E2, whatever, as many as you want to have embedding dimensions, target dimensions. Let's say you want to embed it into a two-dimensional space, so you take the so L0 you discard because this is going to be 0. Let's say L1 is already a non-zero eigenvector, L2 is the second smallest non-zero eigenvalue. Sorry, L1 is a non-zero eigenvalue. The smallest one, L2, is the second smallest non-zero eigenvalue. The associated eigenvectors are E1 and E2. They have n entries if you have n samples. So what you can do is you write them into a matrix. Yeah, as I say, so they have n entries. If you have n samples. Now, if we're looking for the ith entries of the, sorry, if we want to project xi, sorry. If we want to project xi into this lower dimensional space, then we check for the ith row and we take these two values. Yeah, so this is the lower dimensional embedding, then E1i, E2i. These are the lower dimensional coordinates. That you use for the embedding. Okay, so it's a very simple procedure. You calculate L, you do the eigenvalue decomposition, you pick your smallest eigenvectors, you take for every sample, you take the corresponding row from the eigenvectors, and you're done. Okay. So this concludes it for today. We can talk about more details about the classification and regression trees and the random forests in our joint meeting. I'm looking forward to meeting you then. Thank you. Bye-bye.